So perhaps the most significant technological or biotechnological development in the past 50 years is the polymerase chain reaction. And I know that some of y'all probably have exposure from maybe your genetics class where you talked about PCR. But I'm going to go over it a little bit here as well, and put it in the context of this class. So PCR is used to amplify DNA in a test tube. So an in vitro amplification of one piece of DNA. Now, what this is going to consist of is a couple of different things. What you're going to have is the target or the template piece of DNA. You're also going to have what are known as primers. Then you're going to use your deoxynucleotide triphosphates, DATP, DCTP, DGTP, DTTP. Key is deoxy because we're synthesizing DNA. In addition to that, you're going to have a thermostable DNA polymerase. And the reason for that is because of the cycling of these steps. So what you will do is first melt your DNA for about a minute to 2 minutes at 95 degrees Celsius. Then you will cool that DNA. So what's happening here is you're taking this double-stranded piece of DNA, and then what you are getting is 2 single-stranded pieces of DNA. So your second step is to cool those strands to about 50 to 60 degrees. At this point, your primers, your synthetic oligonucleotides, will bind to the complementary region on these 2 strands of DNA. Now, so you heat it up to separate these 2 long strands of DNA, or this one long strand of DNA into 2 individual strands. Then you cool it down so your primers can bind. Once those primers bind, which again, this is about 30 seconds or so, then your polymerase is actually going to carry out its function, and it's going to polymerize and make these new pieces of DNA. Now, in that process, and this is going to be made in the 5' to 3' direction, this is the elongation step. So you have the steps are basically known as denaturing, annealing, and elongation. Now, some of the terms here are interchangeable, or maybe you've heard different terms. For instance, the first step of denaturing, that could also be your melting step. The second step, the annealing, could also be a cooling step, and the elongation could also be a polymerization step. Now, what you have is temperature cycles from 95 degrees to 50 degrees to 72 degrees. Now, the temperature isn't mentioned for this elongation step, but basically what that means is you go from very high temperature, almost boiling, to 50 degrees to 72. And then you repeat it over and over and over and over again. And we're going to see a visual of that in just a moment. But what's important here is this is all in one test tube. So what that means is that this DNA polymerase and everything else in here has to be stable at, or has to be able to endure a 95 degree heating, a cooling, back to 72 degrees. So this is a visual of what's taking place. We've got our double-strand piece of DNA that separates. Our primers bind right here. The primers are indicated by these little yellow squares. Then our DNA polymerase produces our new polymer. And that new polymer, keep in mind, it's going in the 5' to 3' direction. So it's going to start at one place and it's going to extend. It's going to start and extend. Those subsequent steps will be cycled over and over and over and over again. Generally, PCR is done about 30 to 35 cycles, where you have the same cycling of heating, cooling, polymerizing, heating, cooling, polymerizing, heating, cooling, polymerizing. They just go over and over and over again. That DNA polymerase is only going to be doing something at that polymerization step. So it is in there, so it has to be able to endure heating up to 95 degrees Celsius. So if you were to take human DNA polymerase, that wouldn't work because you wouldn't be able to heat it to 95 degrees and it then be functional at 72 degrees. So that's why you have to have that thermostable polymerase. Now, you're going to repeat these steps many times. This says 25 cycles. I would argue anywhere from 25 to 35 is going to be fine. But ultimately what you're going to do is going to go from 1 piece to 2 pieces to 4 to 16 to more than 16. What was 16 to, I think that would be 256. I think so. Anyway, you're going to continue this over and over again. And so just from, let's see, that would be 1 cycle, 2 cycles, 3 cycles, 4 cycles. From 4 cycles, we've basically perfectly amplified 1 piece of DNA and made 256 out of them. So you're going to have huge numbers of pieces of DNA in the mix.